Welcome back to KIN 390, Exercise Physiology. Today we're going to continue with Lecture 5. We're still working with bioenergetics, or the energy of life, if you will. This is part 2. So we'll continue today with discussing fuel. And we left off last time with this slide. So let me just bring this guy back up for you here and give you kind of a summary. I think at this point we kind of get the big picture, and where we're talking about the consumption of food, of course, is the first step to a myriad of chemical reactions that are going to happen in your body to resynthesize adenosine triphosphate, ATP. Of course, what has to happen is once we reassemble that ATP, we're going to break it down again. And this story, I hope, is sounding like a broken record, or I'm sounding like a broken record, and this is sounding very, very familiar, because the only energy, free energy, that we can use for biological work, or work in biological systems, which is the human body, is the energy released from the breakdown of ATP. We also discussed the fact that ATP is stored a little bit. We do have a little bit of storage, and we'll talk more about that today. But generally what has to happen is you have to be continuously resynthesizing ATP all day long for every cell, and breaking it down again. Where most of our ATP resynthesis starts with, or what starts our ATP resynthesis, are macronutrients, and primarily carbohydrates and fat. Don't forget protein. We even kind of ignore it to some degree in bioenergetics, because if you are eating a well-balanced diet that includes carbohydrates and fat, as we still absolutely recommend, then protein is really not going to contribute to much ATP resynthesis throughout the day. And in class, I believe I shared with you, most estimates on a well-fed human or a normally fed human would be 2 to 15% of your ATP each day is resynthesized from protein. Very little, then, right? So even if you're at the high end of 15%, that means 85% of your ATP resynthesis through the day happened from carbohydrates and fats. Last class, we also discussed that carbohydrates are used during moderate to intense activity. They must be used. But the storage of them, glycogen, is limited. It's still quite a bit. I mean, we can still, travel 20, 25 miles on those glycogen stores. But we do, if we're going to go further than that, which is common nowadays with our ultra and endurance events, we have to replenish those. Fat, however, we have a lot of. Even with this 12% body fat example, we do have a lot of fat stored. Remember I shouldn't say the problem. Remember, what's going on with that, though, is that we really only use fat during rest and low intensity activity as our primary fuel source. We can and we do use all of them all the time, but we just don't use very much at certain times. But fat takes a long time. It's a little bit more of a complex process to fully break down fat into what it needs to be, its substrate, to get it to resynthesize ATP. So although we have a lot of it, we have a lot of potential there. Remember, we measure that in kcals. Fat is going to be one of those things that you'll use a lot when you're resting, but you're just not going to use very much, or very, very low intensity activities of daily living, like putting groceries away or something like that. You'll use mostly fat. Just like I said, the thing is, you're not going to be using very much because it's not very intense. So that brings us to here. This is our next layer. And we have gotten a little deeper, but I'll remind you here of a couple of concepts. Metabolism is the sum of all the chemical reactions in the human body. Most of the time, when we're talking about metabolism, we are talking about those catabolic reactions. And for us, what we're talking about, of course, is the resynthesis of ATP. What really has to happen, though, is a series of reactions, pathways, if you will. So if you think of a pathway, I often think of a journey. Like you're going from point A to point B. You're getting there, if you will. So if we want to get to ATP, we have to take a bunch of steps to get to where we want to go. And so in general, we have three big classes of pathways. Those three classes, if you will, and they're not really called classes. They're called, they're kind of grouped together. But the three big groups are the phosphagen pathways, the glycolytic pathways, and the oxidative pathways. Within each of these, there are several metabolic pathways that are going to lead to the resynthesis of ATP. And that might feel a little confusing right now. It's okay. Let's get through the detail or some of the details here, and then we're going to do an activity that I think is going to really help solidify what I mean by this. But what I'm talking about is a series of chemical reactions that start with something and end with ATP. Those are energy pathways. You can also call them metabolic pathways. You can call them energy systems. I've heard that. I think your textbook might use energy systems. That's fine. But all we're talking about is starting with something and ending with ATP. And there's a multitude of reactions that occur along the way. We're going to start with the phosphagen system. And the phosphagen system is also often called the ATP-PCR system or the ATP-CP system. And PCR stands for phosphocreatine, or CP, it's the same thing, creatine phosphate. So we often call these the same thing. If you have a pathway that happens and it's with what we would consider phosphagen-based, is these are going to happen in the cytoplasm. For us, we talk about muscle most often, so that's the sarcoplasm, because we're dealing with muscle cells, right? Sarcoplasm. So these pathways happen in the sarcoplasm, and they're anaerobic, which means they do not require oxygen to take place. So there's no step in these pathways that requires oxygen for it to be completed. The glycolytic system is the next one we'll discuss. And this is an interesting group because we're talking about glycolysis. Glycolysis is the breakdown of glucose. It begins in the cytoplasm, or it begins in the sarcoplasm, but then the products that you get from some of those reactions can go into the oxidative system. And if they go into the oxidative system, that means that they've entered the mitochondria. So the glycolytic system itself, technically, the first 10 steps of glycolysis are within the sarcoplasm, and that is anaerobic. Just remember this. If it's in the sarcoplasm and it's a metabolic pathway, it does not require oxygen. Mitochondria, if something's in the mitochondria, I should say, that means it requires oxygen. And when we call that aerobic. So oxidative, aerobic, what we're saying here, these are the metabolic pathways that require oxygen. So let's start with the phosphagen system. The phosphagen system here, you'll see the three main ways that we are going to resynthesize ATP. The first is you do have a little ATP stored in cells. So you can go right to that and use it if you need to. You can also use creatine phosphate, and you can also, there's a myokinase reaction that we'll briefly discuss, and that can yield you some ATP as well. Then we've got glycolysis. Again, it is anaerobic because the first 10 steps are in the sarcoplasm. But then you can also take, and we'll talk about this, you can take pyruvate and put it into the mitochondria or shuttle it into the mitochondria. And as soon as it's in the mitochondria, now we're talking about aerobic pathways. And then within the aerobic pathways, what we're talking about are the Krebs cycle and the electron transport chain. Okay? So aerobic. It is important to remember that there are what I call two rules for energy systems. And those energy systems, or those energy system rules, are, number one, all energy systems are active at all times. There are no on-off switches. Now, what often happens is that one will predominate. That's a very important word. One will predominate depending on what you are doing. So, for example, this graphic is a very famous one, or a very popular one, and it is showing you that the longer the exercise goes, then the more reliance you will have to have on aerobic energy systems. Really short-term stuff, for example, on that left side, really short-term stuff, you're looking at ATP creatine phosphate or phosphocreatine. So that's rule number one. All energy systems are active at all times. This is another example of that, and it shows that depending on the duration of the exercise, and what we're talking about here is exhaustive exercise. So this is high intensity exercise, 0 to 10 seconds, you'll see there, mostly anaerobic. 94% of your ATP resynthesis is anaerobic. You go up to 240 seconds of intense activity, and you'll see there that although we're going to contribute somewhat to ATP production from anaerobic sources, because of the duration, aerobic has really had to come in and become the main person there, the main driver. And so if you are now at exercise that is at 4 minutes plus, aerobic is going to be much more of a contributing factor when it comes to the resynthesis of ATP. So that's rule one. Rule one for energy systems. Write that down. Make a note. All energy systems overlap. All energy systems are active at all times. Let me say it one more time. These are not on-off switches. These are metabolic pathways. So none of them stop. But rule number two is that they all, that depending on the time or the intensity, and I'll re-say this, I apologize, I fumbled. Depending on the time and the intensity of the exercise, you will have one or two predominate. So let me go back. Rule one for energy systems, they all overlap. They're active at all times. Rule two is that depending on duration and intensity of exercise, one system may predominate. So let's get into these. The phosphagen system is by far the simplest of the three energy systems. Besides ATP, so you do have a little ATP. If you take that ATP, it's ready to go. So it is included in the phosphagen system, but the first part is you can use the itty bitty bit of ATP stored in the cells and break off that last phosphagen. You can also use another high energy compound called phosphocreatine, also called creatine phosphate, and typically, I'll just let you know, I say CP, creatine phosphate. It's just kind of how I learned it and it's stuck. But they're the same thing. They're the same molecule, if you will, or compound. It's a compound. You don't have much of it, but you can use it in really high intensity exercise and when you need ATP quickly. It is anaerobic because it does not require oxygen. It doesn't mean that oxygen is not around. That's really important. Oxygen is always around because cells that don't have oxygen die. But the phosphagen process, the step-by-step process to resynthesize ATP, does not require it. That's really important to understand. It's there. You're not deprived of oxygen. It's just that you don't need it for that reaction. So the energy to reassemble, remember the point here, so you do have some ATP stored in cells. And that's great, and you can right away take it and break it down. But what has to happen for creatine phosphate is you're going to take one creatine phosphate molecule or compound, and you're going to break the creatine and the phosphate apart, and then you're going to use the phosphate to reassemble ATP. So here's this picture here. So what you've got is the phosphocreatine is going to break apart into a creatine molecule and then its inorganic phosphate. And then look at this. What has to happen? Another reaction where you take an ADP, combine it with that free phosphate, and create ATP. And I think you'll recognize now that this kind of reaction is an endergonic reaction, right? So this is a coupled reaction. So let me go back. The coupled reaction here is that phosphocreatine is going to give off free energy and break apart its creatine and its phosphate. So that's an exergonic reaction. And then ADP and PI being put back together using that free energy is an endergonic reaction. And the purpose of the breakdown of this creatine phosphate is to supply energy for the resynthesis of ATP. I think this is a wonderful graphic. So what drives this reaction? It is a it's an enzyme, creatine kinase. Creatine kinase is going to, just like ATPase that breaks apart or breaks off that last phosphate, creatine kinase is going to help us break that phosphocreatine into creatine and PI. Which brings something up here that we haven't quite talked about with our reactions. How do they know, I'm kind of oversimplifying this, but how do they know when to start and when to stop? Well, that is because of the mass action effect. So the concentrations or the amounts of reactants or products, or both, will drive the direction of reactions. What I mean by that? So for example, if in a cell we have a lot of ADP and a lot of phosphagens, a lot of inorganic phosphates out there, what's going to happen? Well, we're going to put those together. So that increased concentration is going to lead to the increase in creatine kinase activity. However, the opposite is true. Let's say there's plenty of ATP put together in that cell. Well, we can slow down that creatine kinase activity then. So that is the mass action effect, and that's how a lot of these reactions work. We'll talk about another example a little later. Like ATP that's stored in the muscle cells, phosphocreatine stores are very limited. And I don't think I mentioned this, but I think this is an important point here. During really intense exercise, if you are all out, like an explosive jump or a shot put, you would use the ATP stored in the cells. You need it immediately. You need to move very quickly and very powerfully. But you only have a couple of seconds worth of ATP stored in your cells. What I mean by that is if I was able to say, you cannot use any other metabolic pathways to create ATP, you can only use the ATP stored in your muscle cells, you would be able to move for 3 seconds. Take that in for a second. I'm going to re-say it. If you could not resynthesize ATP by any other means, you had to only use what's stored in your cells, you would be able to move for 3 seconds. And remember why? It's really heavy, right? It's really heavy. So ATP is inefficient for us to store. What we need to do then is resynthesize it. So now, thinking about the next step, okay, let's say you want to move for more than 3 seconds at a real high intensity. You do have creatine phosphate available to you. It's still very limited. So during intense, all-out muscular activity, there's actually only about 3 to 15 seconds worth of creatine phosphate. And this is intense, all-out muscular activity. So you can think of that like, okay, if a shot put is, I do an all-out put and it only takes 1 second or 2 seconds and I've used the ATP stored in my muscles, then if I were going to continue to do that, I would have to go to something else that was really quick and easy to use. The phosphagen system then, or the creatine phosphate, would be used. A good example would be like an elite 100-meter sprint, which is about 10 seconds for our elites or less. But even amongst men and women, an elite 100 meters is around 10 seconds. So you need it quick, you need it immediately, and so you would use the creatine phosphate stored in your cells to complete that task, or the bulk of that task, because remember, rule 1 is they all overlap. But in something like a 100-meter sprint, creatine phosphate's by far going to be your predominant energy source. But most things in our world, if you think of that, those two examples of a shot put for ATP and a 100-meter sprint for creatine phosphate, those aren't happening that often. I mean, it is for those athletes, but really we need energy for typically longer and usually less intense activities. So then we turn to the other two energy systems to resynthesize our ATP. So showing you here ATP and creatine phosphate amounts in type 2 muscle fibers, which of course are the types of cells that we would use for explosive maximal exercise. You can see by 14 seconds out, these stores are gone, right? So creatine phosphate, dropping off pretty quickly, ATP dropping off really quickly. And so if you're at intense exercise, maximal exercise, 14 seconds, it's gone. It's gone within that amount of time. This is a great graphic. So to keep going, what do you have to do? Well, chances are you've got to stop or slow down. So let's say you do sprint for 14 seconds. You can still move after that, right? But you probably aren't really all out sprinting for much longer than that. So you do have to stop or slow down. You could easily go to a walk or a jog and keep sprinting for much longer. So another key component in the phosphagen system is the myokinase reaction. So, here, let me go here. The myokinase reaction can actually take ADPs that are floating around in the cytoplasm and take one of its phosphates, essentially, and reassemble ATP, and then you have adenosine monophosphate, AMP. So that is something that can be present in cells. But there has to be a lot of ADP around for this to happen in high amounts. So if there's a lot of this going on, that means you really need a lot of ATP quickly. But if you have AMP around, so if this has happened, AMP, adenosine monophosphate, is a very powerful stimulator of other energy systems. Boom. So there's the next one. So let's just go back here for a second. Think about the phosphagen system. So I'm going to wrap it kind of up for you. So the phosphagen system technically has 3 different things you can do. You can use the ATP stored in muscle cells. You only have a few seconds worth of that. and and you're going to only use that when it's really high intensity effort. You can then go to the creatine phosphate pathway, and you can break that molecule apart, or that compound apart, and resynthesize ATP. That you have for about 3 to 15 seconds, and again, this is high intensity maximal effort. Or you can go and then you will go to this myokinase reaction, where you will have a lot of ADP around, and you're going to put together ATP from that. Once we have a lot of AMP around, the other energy systems are going to kind of wake up, for lack of a better term. And so phosphagen is ATP stored in cells, creatine phosphate, and the myokinase reaction. Like I said, though, most of the time we're not sprinting through our days, and so the other systems are used quite a bit. The next one in our series of 3 big groups is the glycolytic system. The glycolytic system supplies energy for the resynthesis of ATP, just like every other metabolic pathway that we've discussed. But in the glycolytic system, we're only looking at glucose, only, or carbohydrate. You can think of it as carbohydrate, but really, glycolysis starts with glucose or glycogen. So glucose is broken down through this process of glycolysis. And just in case, you can always figure out or try to figure out what words mean in science by knowing some prefixes and suffixes. And so lysis is going to mean to break down or dissolve. Glyco, it means carbs, sugars, carb sugars. So glucose is supplied from the breakdown of those dietary carbs that we've talked about. It's used immediately for energy for the resynthesis of ATP, but we can also store it in muscles and liver as glycogen, as we discussed last time, until it's needed later. Or it can, this isn't a complete detailed discussion, but it can be stored as fat. It's got to go through some other processes, but if you have too much of anything, you can store something away as fat, typically. When you're going to take that glucose and store it away to glycogen, that is called glycogenesis. So now genesis, creation. And glycogen is really just a long branch chain of glucose molecules. So glycogenesis is we're going to store it away. And typically, and you saw this actually, the last thing that we talked about in part 1 was the fact that you really didn't have much blood glucose ready for you. Most of the time, you're going to have to pull from your liver and your muscle cells. So glycogenesis is happening quite a bit, and most of the time, you're going to have to pull glycogen for glycolysis to occur. When you take those glycogen stores and break them back down to glucose, that's glycogenolysis. Glycogenolysis. Again, lysis, breakdown, dissolve. Glycogen is in the word, right? Glycogenolysis is the breakdown of glycogen to glucose. Then what can happen, so you can take glucose from the blood and do this system. Like I said, that just doesn't happen as often. Most of the time it's glycogen, but you can take both, and once you get glycogen broken down to glucose, you can do about 10 steps, and we can produce a couple of moles of ATP. So we can produce a couple of moles of ATP from glucose itself. In the cytoplasm, so this is anaerobic, the first 10 steps of glycolysis occur. I'm going to say that again. In the cytoplasm, the first 10 steps of glycolysis occur. The end product of this 10-step glycolytic pathway is pyruvate. Pyruvate. And you may have heard of it as pyruvic acid. Technically, they're different. Chemists would probably not like this. Acids and salts are different, of course, but pyruvic acid gets produced and then is quickly turned to pyruvate. So check this out. So this is the 10 steps. Do you need to know every single step? No. What are the important parts? We start with a glucose. And you'll notice in the first, so every number represents a chemical reaction. Number 1, look at what's going on here. You're trying to synthesize ATP, but what happens is that you actually need ATP to start this process, believe it or not. So you're going to do an exergonic reaction. You're going to break down ATP and donate that phosphate to the glucose that you start with, and then it becomes glucose 6-phosphate. Okay, for muscle glycogen, this is something that Dr. Beckham added. I'm not going to worry about it too much, but for muscle glycogen, it's glucose 1-phosphate because my muscle glycogen is a storage form, so it is a little different. We don't need to worry about that though. Next step happens, and you see, then we have to donate another phosphagen, okay, to that process, to that third step. And from here, we get two. We get 2 compounds of 3-phosphoglyceraldehyde. Say that fast 3 times, huh? And from there, then these reactions happen twice, but simultaneously. So at the top, you'll notice, and phosphofructokinase, by the way, PFK, is the enzyme that is a rate-limiting enzyme for this reaction. And I'll talk about that here in a second. So that's why it's there. But then you'll notice, okay, at the top, and remember this is all happening in the cytoplasm, at the top we have an investment, if you will, of 2 ATP. And then once we break apart here and do the last 5 steps, we get 4 ATP out of those reactions. So you invested 2 and you got 4, which means that your net gain of ATP for glycolysis, or anaerobic glycolysis, because this is happening in cytoplasm, is 2 ATP, 2 molecules or moles of ATP. There are other important things that happen in this reaction, or in these series of reactions, this pathway. And you'll notice here, for instance, things like NADH and hydrogen get shuttled to the electron transport chain. And we'll talk about why that's important here in a second. But what happens is that you get 2 moles of pyruvate from this reaction. And from here, these first 10 steps, if you're moving really, really, really quickly and very, very intense effort, the pyruvate is going to be converted to lactate. So it's going to go through another reaction. So if you're moving really quickly and you're staying within this anaerobic reaction, pyruvate becomes lactate. And I'm sure all of us have heard about lactic acid. So this is where it comes from, is after the first 10 steps of anaerobic glycolysis, if you're moving very, very, very fast and 100% effort, that pyruvate becomes lactate. And if you don't know what that feels like, go ahead and go out to your road or your street and sprint for as long as you can. Try to get at least 30 to 45 seconds out of that sprint. Okay? Yeah. Or if you're on a bike and you pedal as hard as you possibly can with the resistance up a bit, do that for 30 to 45 seconds. You're going to produce a lot of lactate, and you will feel it. You will feel it. But we'll get there. We're going to actually talk about lactate. But for now, let's kind of reconvene here. First 10 steps, anaerobic glycolysis, you are going to get pyruvate that can become lactate if you're doing real intense exercise. But if you're not doing very, very intense exercise, you're just doing long exercise, then that pyruvate is actually going to go into the Krebs cycle. Okay. So the process of glycolysis that does not require oxygen is anaerobic glycolysis. But of course, aerobic glycolysis is possible, and we'll talk about when that kicks in here in a second. But just to make sure I'm staying on task, that pyruvate, as I mentioned, can convert to lactate. And same thing, lactic acid and lactate, we use it interchangeably a lot in exercise physiology, although technically they are different. So this whole thing here is just showing you the overarching processes of taking glycogen from muscle, which is what most commonly happens unless you're asleep. You got to break that down to glucose, or you take blood glucose, but you just don't have very much of it. You take it through that 10-step sequence, which will get you a couple of moles of ATP. It will also then get you pyruvate or pyruvic acid, and if you're moving very intensely or 100% effort, it will go to lactate. Pyruvate is converted to lactate, again, when not enough oxygen is present to prevent it. And so you can use lactate elsewhere. So a lot of times, or you'll hear, you'll maybe hear the little joke that lactic acid is not the enemy, and it's not. The upside is that it runs really quickly, right? And it can be taken to other places. But the downside of this fast glycolysis is that you really don't get much ATP. You can't run as long because of the high production of lactate, which is going to mean an increased acidity. So your pH is going to drop if you have the breakdown of ATP and other anaerobic processes. So there's pros and cons, but you absolutely have to use this if you're going to be moving quickly for 30 to 45 seconds. Aerobic or slow glycolysis, I like how Dr. Beckham uses slow glycolysis. As I mentioned, if you're not doing something all out, like super intensely for 45 seconds or 30 seconds, and you're moving a little bit slower, and you're doing this for a while, like 3 minutes plus, then what can happen is that pyruvate can convert to acetyl-CoA. And when that happens, acetyl-CoA can then enter the oxidative system. So now it can be moved into the mitochondria. The upside, of course, you're going to get a lot more ATP from the oxidative system. The downside, it takes more time because now we're going to be putting in a lot more complicated processes or pathways with oxidation. Okay, so what controls glycolysis? Don't forget that they're pretty much the same. Anaerobic and aerobic glycolysis, they're the same. They start with the first 10 steps, right, of anaerobic glycolysis, but the fate of pyruvate is different. The fate of pyruvate is different. So here we go. PFK is the rate-limiting enzyme in glycolysis. So what happens here is if we have a lot of AMP, if we have a lot of ADP, and we have a lot of free phosphates in the cell, that means that, hey, we probably need more ATP. So let's increase PFK, phosphofructokinase. Let's increase that activity and put these guys together. If we have a lot of ATP and creatine phosphate, that means that we have enough, maybe. Then what's going to happen is that PFK activity will go down, just like the example from earlier with the myokinase reaction. So prolonged, extremely high ATP breakdown results in increased acidity, which slows everything down. So here we are again. We are pretty much in the middle of glycolysis, meaning we've talked about the phosphagen system today, or those pathways, and we've talked about the first 10 steps of glycolysis, and that it ends with either pyruvate or lactate. But if that pyruvate gets converted into acetyl-CoA, now we're here. Okay, now we're in aerobic glycolysis, but it still starts with the first 10 steps outside of the mitochondria. Okay, so that pyruvate, though, like I said, if it's converted, I think I just said this. Sorry, I got ahead of myself. Losing it. So that acetyl-CoA can enter the third, which is the oxidative system. Okay, so I'm just going to repeat for one more time. I know you're probably really sick of hearing this, but anaerobic happens in the cytoplasm. Aerobic happens in the mitochondria. The phosphagen system is going to be used when you need energy really, really quickly. So you're going to be doing things that are maximal effort. ATP, creatine phosphate, myokinase. But if you're going to do something high effort for a little longer, you've got to do anaerobic glycolysis, which is the first 10 steps of glycolysis in, of course, the cytoplasm. You get pyruvate from that. You get a little ATP. If you're moving really quick, that pyruvate's going to go to lactate. But if you're not moving too quick, let's say you're just out for a really easy jog, then that pyruvate is going to be converted to acetyl-CoA and now enter the mitochondria, and immediately it becomes an aerobic pathway because these guys are all going to require oxygen. I think that's good for part 2, so I'm going to go ahead and shut this down for today. Of course, you're moving at your own pace, so if you want to continue on, great. But I am going to go ahead and do a part 3 of this video so that you can, again, break this down into manageable chunks. At any time, email me. Questions, comments, concerns. We are doing our best here, so you just keep doing your best and read your textbook. I think it's a great textbook to complement some of the things I'm talking about, and of course you can slow it down, read at your own pace, do the activities and the terms within that textbook that are going to help solidify this information to you in this online environment. I realize a lot of you are probably not, or I should say you're probably familiar with online learning, but some of us don't like it, and that's okay. We're doing our best. So just use all the tools at your disposal, including that textbook or the online modules that maybe came along with your textbook, okay? All right, so for now, that is part 2, and you'll hear me again for part 3. Have a good one.